All right, so today we'll start looking at chapter 6, which is our introduction to discrete probability distributions. So in this chapter, we will be introducing two incredibly important new concepts. Almost everything that we do from this point on will be based on these two ideas, which are random variables and probability distributions. So let's start with the random variables. Now, what happens here is that when you have some kind of an experiment taking place that generates outcomes, sometimes the outcomes, as we've seen, might be letters or numbers or colors or anything you could imagine, but it's usually more convenient to have numbers assigned to the outcomes of an experiment. So that, for example, when we were rolling the dice in the last couple of examples, the outcomes were E and O. If we were flipping a coin, the outcomes would be heads and tails and that type of thing. What a random variable actually does in a nutshell is that it assigns numbers to those outcomes, because numbers are a lot more convenient to deal with than letters, okay, or anything else for that matter. So all we're really doing here is assigning numbers to the outcomes of an experiment, but we're doing so not in an arbitrary fashion, but we're using a specific set of rules to assign those numbers. So the name random variable really is not very accurate at all, because there's nothing random about it. What's really happening here is that this is what we could think of as a function. It says, give me the outcomes of an experiment and I will assign numbers to those outcomes. So for example, suppose we're rolling the die twice, as we've been doing up to this point, and we're looking at whether or not the number is odd or even. And so suppose that I define a random variable x as the number of times an even number turns up during the experiment. Well, what we can do then is assign each possible outcome of this experiment to a single number, which represents how many even numbers turned up. So here's the chart, and you can see pretty clearly here that if we end up with an EE, or two evens, then x will be 2. In other words, 2 is assigned to this outcome because it has 2 even numbers. If we get either EO or OE, then x assigns a value of 1 because there's clearly only one even number. And then, of course, if we get 2 odds, then x is 0 because there are no even numbers. And it's really that simple. So literally all x is doing is taking each of these sample points or outcomes and assigning it a number, which represents how many evens turned up. Now, we can define this any way we'd like. We could have just as easily assigned the number of odds or anything you could imagine, but here we're keeping it simple. We're just going to let x represent the number of evens. Now, why do we need to do this? Because this makes it easier to calculate probabilities. This is really the point of a random variable, to make it easier to calculate probabilities than dealing with a bunch of letters. Now, this case is very simple, but if we were to roll that dice, let's say 10 times, we would have an enormous sample space, and then dealing with the letters directly would become very awkward. So that's why having a random variable is a very convenient thing to do when we want to calculate probabilities. Now, if you look at these carefully, and if you recall, these are all equally likely to occur. Since x assigns 0 to the outcome OO, it stands to reason then that the probability that x actually equals 0 is 1/4. Why is that? Because there's only one way we can get no evens out of 4 equally likely outcomes, which means therefore this probability must be 1/4, or of course 0.25. Now, and of course, this is based on the assumption that the dice are set up so that all sides are equally likely. There's 3 evens, there's 3 odds on each die. So therefore, this is going to have a probability of 1/4. Now, x equals 1 is different because there's 2 ways that can happen. Okay, we can either get EO or OE, each of which is equally likely. Okay, so therefore, the probability that x equals 1 is the same thing as saying getting exactly 1 even number, and that is therefore 2 out of 4, because there's 2 ways this can happen. Both of these are equally likely. All right, and then finally, what's the probability that x equals 2? Well, that's 1/4, because again, there's only one way this can happen. In order to get x equals 2, we must have 2 even numbers. So what we've done here, we've accomplished actually quite a bit already. We've introduced the concept of the random variable, and you can see it's not that difficult. It's just simply a way of assigning numbers based on a specific rule. In this case, the rule is right here. Okay, and we can define this any way we like, but of course there are certain requirements here that we have to follow. First of all, we cannot have any negative probabilities, as you know from the axioms of probability. And we have to make sure that we've assigned X or defined it very carefully, because we have to make sure that the sum of all of these probabilities has to be exactly equal to 1. Okay, now that is the case here, as you can see that this probability is a quarter, 2 quarters and 1 quarter, which of course do add up to 1. Okay, if that isn't the case, then there's something wrong with the way we defined a random variable, and we have to do something different. Okay, now, discrete. The word discrete here simply means that X, whatever it is, whatever it represents, can only attain a finite number of different values. Okay, in other words, like here, for example, X can only be either 0, 1, or 2. And therefore, the X we've just defined must be discrete. Okay, discrete simply means the opposite of continuous, which we'll see in the next chapter. If X is continuous, what that means is that it can have literally an infinite number of different values. All right, so we'll save that for chapter 7, by the way. Now, we did mention up front that we're defining 2 important concepts in this chapter. Random variable, again, which just simply assigns numbers to the outcomes of an experiment. Now, a probability distribution takes this one step further and says, you know what? Why don't we take all of the outcomes of our experiment, assign them numbers, and then we're going to create a chart or a function which assigns probabilities to those outcomes. Now, for example, here, what we could do here is create a little chart. Let's do this. Let's see if I can do a little table real fast. Oh, sorry about that. Now, you notice how it gives me green. I didn't really want green, but that's what it defaults to. I have no idea why. You would think somebody at Microsoft would have noticed this and said, wait a minute. Green, are you kidding? But that's not how they think over there, apparently. So let me see if I can find a nice table for us. One that doesn't look so ridiculous. Like this one. Okay. All right, so here's X. Here's the probability of X. Okay. Now, what exactly is going on here in this chart? What I want to do is summarize all the possible values of X in one convenient chart, and then the corresponding probabilities. Now, we've already done this. I just want to put it together in one place. 0, 1, 2, if you recall, the probabilities are 1 quarter, 1/2, and 1 quarter. So in fact, this table is a probability distribution. It's a very simple one, but it is in fact what we mean by a probability distribution. Now, if you notice, it does satisfy our requirements. Each probability, let's go find that list again. Each probability is non-negative, which simply means that it's 0 or positive. And all of these numbers add up to 1. Okay, so in other words, we can say that this is valid probability distribution because each individual probability is non-negative and the sum is 1. In addition, this is a discrete distribution because X can only assume a finite number of different values. Okay, so that's what we needed to know. Okay, so this is clearly a very simple example, but it illustrates everything we need to understand about probability distributions, sorry about that, and random variables. Okay, so again, the random variable assigns numbers to the outcomes of the experiment. And in fact, what we could do is have a separate column here that shows the original outcomes. We don't need to do that, but you could do that if you needed to. Okay, and then these are the corresponding probabilities. This table is the probability distribution. Now, later on, we'll see that most of the time we'll not be using tables to represent probability distributions. For the most part, we'll be using formulas, okay, functions. This is only convenient when we have a very, very small number of possible outcomes. But when we get past that point, then we'll want to use typically formulas. Now, I did mention this, I think, the other day, that this is where the calculators start to really come in handy, because several of the standard probability distributions that we'll be studying are already built into your calculators. So a lot of the hardcore calculations can be done directly with your calculators without having to go through all the algebra. But of course, we'll learn the algebra first before I show you all these little shortcuts. All right, that's the way it works. Okay, so let me just straighten this out a little. Anyway, now, you'll recall, because it wasn't that long ago, in fact, it was probably last week, wasn't it, that in our previous chapters, we introduced what were called summary measures, okay? For a sample or a population, we can use summary measures to describe their key properties. These include, okay, measures of central tendency, measures of dispersion, and measures of association. Okay, now we're going to see something similar here for random variables, okay? For random variables, or let's start it this way, in an equivalent way, we can describe a series of measures.
I didn't get that. Could you try again?
A series of measures that are designed to represent the key properties of a random variable. These measures are known as moments. Okay, so it's the same idea. It's just that the terminology can be a little bit different here. Okay, in other words, think of what we're about to do as being equivalent to these measures here, except that because we're dealing with random variables, the way they're calculated will be, of course, different. And in fact, one of the key differences is that these will involve probabilities, which was not the case, of course, with samples and populations. Okay, so what we're about to look at are moments. There's 3 of them. Now, as it turns out, when you see them again, you'll say, oh, these are not very different than what we've been doing. Maybe the names are slightly different, but basically it's the same principle. So we're going to look at the moments of a random variable, and the whole point of these is to understand the key properties of these random variables. So here they are. There's 3 of them. Now, the second and the third ones you recognize right away. The first one, expected value, is simply another name for mean. All right, so in other words, you do know all 3 of these already. The key detail here, though, is that they're calculated in a very different way than what we saw in the previous chapters. Okay, and of course, that's because we're dealing with something very different. In other words, a probability distribution is very different than a population or a sample. So why don't we start at the beginning with the expected value of a random variable. Now, I just want to point out here that these formulas you're about to look at only apply to discrete random variables. The continuous random variables have a set of their own formulas But here we're going to focus on the discrete random variables. So the formulas will, of course, involve some of the notation we've seen before, by which I mean the summation operator. We'll see quite a bit of that. So let's take a look at our first case. The first moment of a random variable x is called the expected value, which is just another name for average or mean. All right, here we go. Now that, if this was last week or before we got started, you might have looked at this and said, ooh, that looks scary. But you notice our old friend, the summation operator here, this EX stands for expected value of X. Now, these X's, these are the individual, or I guess what I should call them is the different possible values of the random variable X. Okay, in other words, if we were to go back and revisit this chart I created here, you could think of this first one as X1, X2, and X3. And it's not really any different than what we did with samples and populations. And then these are the corresponding probabilities. And so I could go back to this chart again and call this one, let's say, PX1, PX2, and PX3. And so that's all it means, okay? You've got for each X, each possible value of X, you've got a probability, of course you do. So what we're basically just going to do is multiply them all together and add them up. Okay, it's quite straightforward. Let's see. All right, so this is the summary of what these, and one more thing, n is the number of possible. It's not a sample size any longer. This is the number of possible values of X. Okay, but again, it's kind of similar. It's just that we're dealing with a random variable now. Instead of a sample size, it represents the number of values X can attain. So in this case, it's a very simple calculation. So remember, we had three possible values for X, 0 1 and 2. Think of this as PX1, PX2, PX3. And based on this chart that we constructed earlier, you can see that this adds up to 1. So what this means, and remember, X represents the number of evens that turned up. This means that on average, whenever we roll the die twice, we'll get one even number. So intuitively, it's pretty clear what this means. Okay, now the variance is, again, closely related to what you saw with the population variance. Formally, it's known as the second central moment. You don't really have to know that. But this is equivalently to a sample or a population. This measures the dispersion of X around its expected value. How spread out can those values get? And this is the formula. Now, this is the formal definition. This is not the formula we will be using. Okay, but this is the formal definition. Now, it turns out that algebraically, this can be rewritten in a way that's much, much more convenient than what you're seeing here. Okay, yeah, you don't want to deal with this. It looks scary because it is scary. Okay, but that's the formal definition. Don't worry, I'm about to show you a very nice, easy formula that will help us get this number. Okay, do you notice, by the way, by convention, we're using Greek letters typically. Remember, we said before, Greek letters are normally used for populations, but Greek letters are also used to represent random variables. Or at least their properties, is what I probably should have said, to represent random variables. So don't be confused here. It should be clear from the context. We're not looking at a population variance. This is a variance of a random variable. All right, so what is this mysterious formula that we're looking for? Okay, and you recall from before, this is the lowercase sigma, and sigma squared is the variance. All right, now this looks a lot like what we did before, doesn't it? So for a population, we have x, this is the population mean up here, which corresponds to the expected value of x. This is squared, we add them up. The difference now is that here we divided by n, and here we're multiplying each term by its own probability. In other words, this is the probability of this particular value of x. That's the main difference. Before, with a population, there are no probabilities. Okay, we're just adding them up and dividing by n. Here we do have probabilities because each x is not necessarily equally likely to occur. So we have to take that into account by using these probabilities. Okay, now here, you see what I've done here. Each x, this is x1. Remember, the expected value of x is 1. This is the probability of x1. Let me clean this up a little. This is x2 minus expected x, which is 1. This is the probability of x2. And then down here, we've got x3. I guess I should include this. And this is the probability of x3. Okay, so then when you do some algebra, well, you can see that this does in fact add up to 1/2. Now, it's very difficult to interpret this in terms of English, but the variance is 1/2. And just like with the samples and populations, the variance is less useful than it might be because it's measured in squared units. So what do we do about it? Well, we have the same solution that we had with samples and populations. We use the standard deviation because it has the same units as the x's themselves. Okay, so if these x's represent evens, the number of evens, then the standard deviation refers to the number of evens. Okay, so we take the square root, just like we did with our discussion about samples and populations. And of course, as you can imagine, this standard deviation of a random variable is designated just plain sigma because it's the square root of sigma squared. And in our last example, remember the variance was 1/2, which implies that the standard deviation must be the square root of that, which is 1/2 or square root of 1/2 or 0.7071. So those are our moments. Now, there are more, but we will not be dealing with them in this course. There's 2 more at least that can be very useful for certain applications, but again, that has to wait till a more advanced class. If you choose to pursue this further, you'll see that there's at least 2 more moments that could be potentially used to describe the properties of a random variable. But here, this is what we really care about. All right. Well, that was a lot to take in. So now, as it turns out, for application purposes, specifically economics and finance, there are many different probability distributions that prove to be very useful for real-world applications. We're going to be introduced to 2 of them here. Now, we chose these 2 because they're very heavily used, not just in finance, not just in economics. They're used in any discipline that uses statistics because the situations they describe are pretty common in the real world. So we're going to start with these 2. And you'll see that they're not terribly complicated, but the formulas can get very involved. So I'm just going to briefly mention them. We're going to be introduced to the so-called binomial distribution and the Poisson distribution. Okay, now binomial, as you can see, the name or the word bi, or the prefix bi, I should say, as you know, by represents 2. So something is going on. Some kind of an experiment is taking place here where there's only 2 possible outcomes. Now, you might not think that that happens a lot in the real world, but we can define a lot of situations where only one of 2 things can happen. And then Poisson is named after the developer, the creator of this Poisson distribution, a Frenchman from, I believe, the 18th century. The Poisson distribution is used to describe how many events occur during a given time interval. Whereas binomial could be used to describe, just as an example, how many heads turn up during a given number of coin flips. That's just an example. It's not a definition, it's an example. The reason why I chose that example is because you can see when you flip a coin, there's only heads or tails. So the binomial distribution would be well suited to helping us understand how many coins or how many heads might turn up when we flip the coin, let's say 10 times or 20 times. Whereas Poisson would be more along the lines of what's the probability that during the next hour, there will be 3 customers coming into the bank. Okay, because that one describes the passage of time. So they're 2 very different distributions, and they do involve a fair amount of calculations, but the calculators that we have will help us along with these. Now, because these are fairly complicated formulas, because it is, let's face it, Christmas break, let's save the rest of this for tomorrow. Tomorrow's Tuesday, the 29th. We'll be back on our normal schedule. And so what I would like to do tomorrow is dive into this rather than try to rush through it right now. So you've got now 2 videos to watch to take the place of Monday's lecture. One of them wraps up chapter 5, and this one introduces chapter 6. Now, of course, when we get back, you'll have every opportunity to ask any questions if you're not sure what we've been doing here. And of course, I'll go back and revisit these concepts to make sure we all understand. But for now, this will be quite enough to get you through today. And then tomorrow you'll be ready for the new content. So I hope you all had a great Christmas, and I will see you tomorrow.